So welcome everyone to this talk. So it's a pleasure to have Priyanka Golia as a speaker today. Priyanka is a faculty member at IIT Delhi, and before this, she was also a faculty member at Cisco Helmholtz Center for Security in Germany. And her main research interests are in the area of like formal methods and its application to AI and essentially the interplay between AI and formal methods. And today she's going to talk about some of her research. So over to you, Priyanka.
Thank you, Shivaji, for the kind introduction as well as the invite. This is my first time visiting Priyanka. I wanted to visit since long, and like, every time I used to meet Shivaji, I was like, I want to visit Priyanka, invite me. So finally, I'm here. And just because we have a lot of PhD students here, so this is my PhD thesis summary sort of a presentation. So I defended my thesis last year in August, exactly a year ago. And then for 3 months, I was at CISPA. Meanwhile, my Indian academia job search was going on, and then I moved to IIT. So today, the talk is going to be about how AI and formal methods can come hand in hand for automated synthesis. This is a joint work with Kuldeep Singh Neil, Shubhojit Roy, and Friedrich Silverstein. So without further ado, let's get started. So the holy grail of programming is what? What we want from our computers to do, that whatever we tell them to do, they do it, right? That's the idea. That's what we want our computers to do it. So the user state the problem and computer solves it. And this is the problem of synthesis, basically, in general. So what we want here? Let's say that there are a set of inputs. Let's call them X. There are n inputs, X1 to Xn. There are m outputs, Y1 to Yn. Okay, let's call them Y inputs. And there is a specification over this input X and output Y. Let's call them Y. This specification. Our goal here is to fill this black box. Now this black box takes input, somehow computes output Y, such that when this X and Y, when you put together back into the specification holds true. That is what we want to do. That is the synthesis task. And this black box can be filled by moving there. There is a way. Okay, let's see how it goes. So this black box can be filled by any program. Of course, we have seen circuits and internal functions. So we can represent each of these output yi in terms of inputs x1 to xn. Right? So for this talk, our task is to come up with these functions, f1 to fn. That's all. So we have inputs, we have outputs, and the specification given to us. We want outputs in terms of inputs such that they satisfy the specification. Let us take a particular example, right? So that everybody is seeing. Let's assume the specification is this. What is the specification? Tells us that the input X is nothing but multiplication of outputs Y1 and Y2. And we say that this Y1 and Y2 cannot be trivially 1. Right? This is the specification given to us. What can we do here? How can we fill this black box? Factorization. Right? If we have in the black box, if we have a factorization algorithm that takes X as an input and gives us non-trivial factors of X in terms of Y1 and Y2, that is going to satisfy the specification. Right? So this specification is given to us and we wanted to come up with a factorization algorithm that satisfies the specification. That's the task. Let us try to formalize it at this moment. So again, inputs always X, X1 to Xn, outputs Y, Y1 to Ym, specification phi over input X and output Y. We want to come up with a function fi corresponding to each output variable yi in terms of inputs such that this weird looking equation holds true. What this equation says? That whenever there exists an output y such that the specification holds true, if we have replaced y by the synthesized functions f, the specification still holds true. So basically, we need y as a function of x such that the specification holds true. And this sort of a functions when we work in a Boolean setting, when x1 and x2 inputs, outputs, and the specification are in the Boolean theory, these are called column functions. And the functions that we are synthesizing, the vector is called column function vector. So our goal is to synthesize column functions.
In the factoring case, what would F be?
What
In the factoring case, what would F be?
F will be the factorization method that takes input x and gives. Right? The F is the factorization method.
How do you write it as a function?
Just output the smaller of the two factors if there is any.
So there exists, right? So you output one factor. You don't need to, smaller is also not needed, one factor. There exists y, it's just says that. And the factorization is a nice algorithm because we don't have here for all x, you see? Why we don't have it for x? Prime, right? If number is prime, then there is no factors. So whenever there exists an output, y such that the specification holds true, that's where, that is the space we want our specification also to hold true with our functions that we have discussed. So if it is a prime number, it can give anything. But if there exist factors, our function should be able to come up with the factors. Right? Toy example. Just again, if I understand that everybody is on the same page, but just to again ensure it. So inputs x1 and x2, output is y1, and the specification is simple. Toy example, right? x1 or x2 or y1. That's it. So one possible, what we want y1 to represent in terms of x1 and x2. So this can be one possible scholar function. Is it this scholar function?
Isn't phi supposed to be a relation?
Yeah, the relation is true whenever the right side is true.
So is it a possible scholar function? Right? So this is P of x, fx, where we have replaced y by this specification, by the functions that we came up with. So this is the f of x, px, f of x. And you see here, whenever there exists a y1 such that the specification was true, the specification in which we have replaced y1 by this function also holds true. Right? So this is one of the possible scholar functions. Is this the only possible scholar function?
Just y1 equal to 1.
Yeah, exactly. So there can exist multiple possible scholar function. For example, negation of x1, negation of x2, and a constant function 1 would also suffice for this particular example. So our goal here is to come up with one such function. We have a follow-up work in which we try to see with respect to the sizes also. But for this talk, it will be just one function that we want to synthesize. Okay? And this problem has a very nice history in the form of existence, not computability, whether there exists such function or with respect to the quantifier, exponential quantifier elimination, Skolem and Hubbard has looked into it. Right? And it goes way beyond actually. George Bull has looked into it with respect to this existence and construction of Boolean unifiers. So this has a very nice story, history, and theoretically, decision version of it, whether there exists such function, not computably, just the existence of these functions are lies into the sigma horizontal. So it's a hard problem. But I come from a theory and practice intersection background, so we do have a lot of approaches that actually works in practice.
Right. So the existence of a function, so the function we want is just the following, right? Like if I don't care about the time, I'm just looking for among all possible y's if something works and I just output the first thing that works.
It's a clear formulation you have seen. So for all x there exists outputs.
Oh, it's like you want the sorry.
It's a two
Yes,
clear
okay.
formulation. In some sense, you are extracting out the strategies. These functions are, if you can, from that point of view, just so it's a hard problem. But practitioners have also looked into it. And there is a lot of work in this direction. varying from extracting from the proof of validity of this formula to the knowledge representation. What is knowledge representation? Coming up with a different form to write this specification that is given to us. And then from different form, try to extract out the functions. Input output separation, incremental recognition, and many more. But what was the problem before we started working on it was the scalability. We were not able to achieve scalability. It was a hard problem theoretically, the practitioners tried, but we were not able to achieve scalability. And when I say scalability, we were able to handle up to 10,000 variables, 10,000 input output cases, but not more than that. That was when I say scalability. That was the case. So there was a gap, scalability, right? To fill that gap, we proposed Manthan.
10,000 means that you can do factoring of 10,000 given number.
Not factoring. So when I say number variable, in terms of number of variables, that's not the right measure to understand the hardness of a problem.
But I would not stand, and you should take as one variable.
Yeah, but then how do you define it?
No, but then if you can.
The factorization up to 14 bits we can handle.
Yeah, but
Basically,
so that I
the
don't understand like what it
right?
means to say 10,000 variables.
Basically, if there is some different structure, not from the factorization is a hard problem, we know, but if the practical instances we have, for example, circuit repair, circuit synthesis, practical instances from the industry, we were able to handle.
There are some instances,
Some
where I can-
instances.
but there are some instances where I can
The
handle one
practical
lakh.
instances from the industry.
Okay.
So industry is not trying to solve the factorization using this way, right? So practical instances from the industry. Intel, Nvidia, where they're developing the chips and they would like to verify it and come up with the chips and circuits.
No, but that's verification. This is different.
So when they are
So
trying
you were
to come up with the
synthesize
chips, the specification is given to you and you want to synthesize a chip. You want to come up with the circuits,
Yeah.
and or gate and also that's what. The verification is different than the synthesis.
No, but yeah, but so then what kind of circuits? So like are
No,
they?
that will answer.
No, but yeah, which like circuits what do we use? And or not is what? So,
Yeah, so and or not.
no, but then why do you synthesize that? No,
The
I'm just trying to understand.
specification is given to you.
Yeah, no, but I'm
So
trying
you
to
say
understand
that-
like what is the circuit with 10,000 input output variables? It's not factoring.
Yeah.
Right.
So, but it's a
So
some
what is it? It's the and or like it cannot be and or not. That I can
controller synthesis, the robots, their path and movement, and then we can do the controller
Oh, okay,
synthesis.
so that's giving the
Yeah.
examples later on. Okay.
Yeah, controller synthesis we have a lot of applications of controller synthesis.
And the specification is given as a book.
Given as an input, yeah, Boolean. So right now we are talking about the Boolean domain. Because the quantification and the Boolean domain itself is very difficult. The people have with respect to this SMTs and all, we have developed the tools with respect to those as well. But for this particular talk, we are going to be limited ourselves to the Boolean domain. It's all Boolean. And or not, and 0, 1, that's it. Nothing.
So the specification is just some relation between the input and output, right? So there's nothing inherently directional about it. It's like in the sense that it's not that y is a function of x or x is a function of y at all in the process. But you want to somehow model that specification by like some directional thing in the sense that given an x, you want to output a y.
Yeah, exactly.
Like an
Such
explicit
that-
function theorem, like, almost feels like.
Feels like, yeah, okay.
What is
No, it feels like an implicit function theorem type statement where you have you have x and y will satisfy an equation potentially psi of x y equals what equals 0 or and from this maybe say okay in my head I'm thinking of this as a polynomial relation. From this I want to express y as a function of x
But if
locally.
we come down into the Boolean domain, then like this equation, but exactly, you are in the right. Yeah. So coming back to Manthan. So Manthan, it works at the intersection of AI, machine learning, constraint sampling and formal methods. I'm going to talk about it. What is constraint sampling? What do we mean by formal methods applying here in machine learning? It's basically a data-driven way to come up with these functions. The framework of Manthan takes this specification that is given to us as an input. And what it does, as I said, we are going to use AI and ML. First, just need to generate the data. Then only we can use that, right? So it generates some data using constraint sampling. Once we have the data, we can come up with candidate functions, right? Those candidate functions we can learn using ML. But these are the candidate functions. We don't know whether they satisfy the specification or not, right? We don't have any idea. It's just some candidate that ML gave us. So we need to have this verification check, right? That verifies whether the candidates that we have are indeed this column function that we wanted or different. If it is different, then we have a counterexample. And with respect to that counterexample, we repair those candidates. So we don't relearn the candidates. Once we have the candidate, we are stuck with it. And we are just trying to repair those candidates. And this repair loop is via formal methods, specifically set SMT solvers. And finally, we get our
I
output.
don't understand. If you can repair, then why don't you just get rid of the candidates to start with a dummy function and keep
But
repairing?
then scalability we were talking about. So some nice guess we want to start with and then proceed.
So you
The
have a
holy
guarantee.
grail was scalability, that's what we
You have a guarantee that this learning process will give you those nice Fs?
guarantee in the sense,
Is it promised to always give you a nice function?
it's a complete, it's nice. We have not defined what we mean by
Yeah, but
nice. We
there-
wanted one function at this moment. And given infinite time, it will converge because this counter example can show that it's the one, once we fix one counter example, it's not going to repeat it. So in terms of a number of input, there can be 2 to the power n counter example. So it's given time, it is complete. But within the timeout, just a minute. Just within the timeout, we just wanted to fill. So whenever we talk about this experimental things and all and scalability, we say that within certain timeout, we want result. And within that, if we want to do that, we need to start with a good guess. We cannot just start with some arbitrary thing. That's the problem. And hence we wanted to come up with a good guess, we are learning the candidates. That's all we are trying to do.
So my question is there, for a specific problem, is there a notion of good that is well defined, and are you guaranteed to always have a function that is good?
No, the notion is defined. We are not guaranteeing that. The notion is in terms of sizes, in terms of number of gates, not the variables and anything, the and or gates that we have. In terms of that, the size is defined and the smaller size circuits are preferable, better than the others.
Okay, so when you say this works, you mean it heuristically works? Because it could happen that the function was not good and then you have to spend a lot of time repairing it?
So again, it's theoretically also complete because
It is
one
complete, that I
example
believe.
is
Yeah.
not
In some time it will eventually.
Yeah, sometime. And what we say, and in the practice, what we see is this: the guess that the Manthan is able to come up with is a nicer guess, so we require less and less number of repairs. So
Okay,
this is just a heuristic again, yes.
okay, yeah,
Yeah.
that's answered.
No, I was just picking up on that question. So, if you didn't use machine learning and started from a clean slate, and you did the same iteration. So, does it in general show that the number of iterations you need?
Yeah, it's more. So not exactly not starting with any need, we started with somewhere in between. I will towards the experimental results, I will talk about that. One case we discussed and where number of repairs were much. So we'll discuss just towards the experiment.
So, your feeling is that machine learning is actually helping.
Helpful, very helpful actually. And not just the machine learning, actually the constraint sampling also, the kind of data that we want is very essential. The ML is the garbage in, garbage out, right? So you need nice data also there. So all of these things are important and we'll see how.
Sorry, what does constraints happen?
Just 2 minutes. So what I'm going to do is that for next 10 minutes, I'm going to give you a quick overview of all of these things. And then again, we'll go back and go into the technical details of these now. Just first 10 minutes, there's a quick overview of each of these.
So for example, this is typically the template that often many of the SAT solvers also follow, right? I mean, in the sense that if you have a SAT formula and you're trying to find a satisfying assignment or prove unsatisfiability, I mean, there's usually this thing
The
of you
partial
start with the
assignment
candidate
and then
thing and then you try.
conflict driven, right?
Okay.
Yeah.
Okay, so it's similar.
Same technique, but now partial assignments we are learning with this, and instead of conflict, we are doing something else. But yeah.
Okay.
Some partial assignment and you get a conflict and you try to repair it. It's essentially the same. Yeah. Okay. Data generation. SAT solvers and satisfiability problem, what was it? It takes a specification and gives us one satisfying assignment. If you ask it to give us 10 satisfying assignment, what is the naive way? You say that get one assignment, block it, try to get another. Block it, try to get another one. Right? but we don't have guarantees that these are uniform. So constraint sampling is a harder problem than satisfiability problem. It says that given a specification, it samples the satisfying assignments uniformly at random. It gives you guarantees that the satisfying assignments that you are getting are uniformly at random.
So every
Again,
satisfying assignment is equally likely to be.
yeah, that is one way. That's what we call uniform sampling. And there are multiple ways of doing weighted sampling also, in which some distribution you can come up with, and you ask your sampler to give us a satisfying assignment as per the distribution. We'll see. So this is what we mean by constraint sampling. We are not generating assignments one after the other in the enumeration way. We are using constraint samplers to give us some data.
How do you deal with the distribution or satisfying assignments without knowing the satisfying assignments?
We'll see. This is just an overview, just 5 minutes based. After that, if you don't understand, we'll see. So uniform sample is of course 1 point, like equal probability for each of the satisfying assignment, and you try to get it. So uniform sampling is relatively easy. Weighted sampling is harder, probably. But that's how we are generating the data. That's what I mean to say here. That's what we mean by constraint sampling. So we get, okay, so this picture, what it is that this is the bigger, this is our search space, and this smaller is our satisfying assignments in the search space, and we are trying to sample our satisfying assignment. That's all. Basically, if we have this specification, we get some data. Each row of this table is a satisfying assignment with respect to the specification. Okay. Once we have the candidate function, what can we do? Because we are dealing with 0-1 cases, the easiest way is decision trees. Right? So what we do? Suppose we want to learn candidates with respect to Y1. We say that X1 and X2 are features, and Y1 is label. We pass it to the decision tree and get our candidate. So from the data, we try to learn the pattern with respect to the inputs. We'll go into the details. This is just for the section. So constraint sampling using constraint samplers, candidate functions using decision trees, and then we try to certify it using SAT solvers. We get a counterexample. We try to extract out the reason why this counterexample exists. What is this counterexample is going to tell you that for this particular input, whatever you have synthesized do not satisfy the specification. Right? That is what our counterexample is going to look like. So when we say do not satisfy the specification, we would like to extract out the reason why it is not satisfying us. That is we do in terms of unsaid core identification. So unsaid core basically tells you the subset of the clauses that are not consistent with each other. So we extract out the reason, use that reason to repair the candidates and this node continues. So this is about the method. The bigger picture of method is this. Data generation using constraint sampling, learning candidate function using decision trees, and then verifying using SAT solvers and repairing using unsaid code. That's what the method is. Now I'm going to go into the technical details of each of these. What nice or not nice that you will judge that we are trying to do here in each of these. Okay. Coming back again to the data generation. What I said that we are going to uniformly at random going to generate the satisfying assignment as per the specification. What is our problem? Problem is that the specification is a relational specification. What do we mean by that? For the same input, there can be multiple variations of the output. Right? Suppose this is our toy example again. This is our specification given to us. Look at these highlighted rows. What it says that when x1 is 0, x2 is 1, both y1 and y2 can take any of these 0, 1 values and they are going to satisfy the specification, right? And if you look at this particular case here, it says that when x1 and x2 are 1, y2 has to take value 0 to satisfy the specification. And similarly, when x1 and x2 are 0, y1 has to take value 1 to satisfy the specification. So this is basically, this table represents all possible satisfying assignments for this specification. Now what are we going to do?
So when we meet satisfying assignments, it's like an assignment to the X's and the Y's. Okay.
That satisfy the specification.
Okay.
So this table basically represents all possible satisfying assignments. We are going to ask uniform sampler to sample some of the satisfying assignment for us, right? That's what.
This table can be enormous.
This table is not given to us. Uniform sampler in general will take the specification as an input and then give you this table there we are.
So this question is still asked, right? How do you generate this?
Yeah.
No, your question was
No,
how do you define the distribution, right? That was your question. It was not about how we generate the constraints.
No, like
that
for
is-
example, suppose the specification was a simple, I don't know, 3CNF or something like that. The task right now is to generate a uniformly random satisfying assignment.
So
No, that is easy.
That is
No, but
that
that's
is not
starting part.
easy.
That's not easy.
Sharply.
That's
But
starting.
It is sharply hard. I mean, conceptually it's easy. You sample random assignment which I will satisfy.
No, you will get 0 most of the time.
Yeah, the distribution you get of satisfying assignments by rejection sampling will be uniform.
so one way.
Yeah, but you obviously want the.
That I would, yes.
So one way to do this is that solution space you divide uniformly at random the solution space using some hash functions, and then with one set you try to sample. Like then once you have the smaller set, you try to sample from that. So that's how the constraint sampling in general works. Uniform sampling. The weighted sampling, why we need, we'll see. Okay, coming back to this. So uniform sampler will take this specification 3CNF, 4CNF, the CNF formula specification as an input and gives you the satisfying assignment. That's it. I asked here that take this specification, give me 4 satisfying assignment. I got these 4 satisfying assignment. Why these 4? Because each assignment in this table had equal probability, so I could get anything.
I want a speaker to have that bots on the slide. Just to mess things
No,
up.
no, I think we need to fix our internet things.
Yeah.
When you invite
So-
me for a talk, I will have a slide with the bots.
So here, coming back to this again. Now you remember what we were planning to do? We were planning to give this as a data for the decision tree algorithm, right? Because the final goal was to come up with the condemned candidates, hence we were generating this data. So think about the case when you pass this data as an input to the decision trees, you might get this as our function. Right? It learned this as 1 and the rest is 0. That's simple. But same time there exist multiple functions and the constant 1 and constant 0 was also one of it. As I said, it's a more heuristical side of the approach, right? So, and this is a toy example. Think about the case when we had lot of variables and satisfying assignments are more and more. We would like to come up with nicer data there so that the candidate function that we learn are easier to repair. Again, it's a heuristical approach, right? We just want to learn nicer, we want to generate nicer data. And what will be the nicer data in this case is this. For all possible assignments, just take y1 as 1 and y2 as 0. So whenever it had a choice between 0 and 1, if it somehow is able to bias it towards 1, then we will be like the data that is going to generate will be good, right? Why bias towards 1 for y2? Because there exists an assignment where it had to take value 1 to satisfy the assignment. It did not have choice between 1 and 0. So whenever it had choice, we say that now because there was one assignment where you did not have choice, can you just go towards 1? So this data will be nicer because we are going to pass this data to the machine learning algorithm to come up with a candidate function. That's all. Hence it is nicer. That's nothing nice in this, right? So if we had this magical sampler that could do this, our job would have been much easier. But we don't have this magical sampler with us.
Sorry, I think what I possibly didn't understand. So are you saying that these constant functions are nicer than the previous ones?
Here, I'm just saying this toy example, we are able to get this nicer 1 and 0. So it will be good for us to generate the data that suppose these nicer functions. But think about the case when we have lots of variables, we just want to come up with a candidate function that require less number of iterations later on. So that means if we have more 1s than 0, then we might have less nicer candidate function or vice versa sort of a setting, but not mix. So whenever it had 0 and 1 choice, we would like it to bias towards 1. We don't want it to randomly sample between 0 and 1. If it's stuck with 1, then whenever it had choice, it should sample 1. That's all we want.
So you want either to be 1 at a very large number of points or 0 at a very large number. You don't want balance.
Balanced. Right? So ideally, the intuition is just this. Whenever a variable had a choice taking value between 0 and 1, we would like it to bias towards one particular value. Every single time. That's it. That's the intuition.
Okay.
In order to not have this kind of balance tree, right? Like equal number of zeros and equal number of 1, that will go past to the machine learning algorithm and then they will learn some random thing. We don't want that to happen. So we can do with this magical sampler, but we don't have that magical sampler with us. So one way, which is to do this, is via weighted sampling.
Why not brute force it? Why not have y1 always be biased to 1 and y2 always be
That
biased?
is not approximation, that is abstraction.
What does it mean?
Abstraction says that for all possible inputs, y1 is going to be 1. Then you repair, saying that whenever it is 0, you are going to repair it.
But that's not what I'm saying. I'm not fixing y1 to be 1. I'm saying when you're trying to optimize for a given variable, you fix whether it will be biased to be 0 or to 1. You will not get 1 all the time, but you will get 1 many more times and you get 0.
So you want to fix it y1 to be 1, right? So
No,
how
I
are
want to fix y1 to be biased towards 1.
Yeah, how are you going to do that? That is all I wanted to say. That's all we are trying.
You want it to be biased towards one.
Suppose we can do that also. We can do that also. It's a heuristic, right?
Yeah.
One of the heuristic is this, that whenever it had choice, I'm just going to say that let's bias it towards 1. Okay, there can be many heuristic. This can be one heuristic. But how are you going to bias y1 towards?
Sorry, question. If you have a choice, you pick it with probability 2/3. That's the bias.
But how are you going to do it in terms of sampling? That's all. That's exactly. If you have choice, you say that with respect to probability, I'm going to put that. So this is where the weighted sampling will come into the picture.
I could think of ways to do it. For example, you could imagine a formula as instead of being over bits, you can imagine being over 0, 1, 2, and both 0 and 1 mean 0, and 2 means 1. Now, if you have a uniform distribution over 0, 1, 2, it's a biased distribution in 0, 1.
I'm sorry.
So suppose you take a formula that is Boolean, supposed to take inputs 0 and 1. I define a formula that is instead supposed to take inputs 0, 1, 2, with the interpretation that both 0 and 1 correspond to 0 in the Boolean and 2 corresponds to 1 in the Boolean.
But then you have the size of the formula will blow.
Yes, a little bit. But the point is that if you now have a uniform distribution over 0 and 2, that corresponds to a biased distribution over 0, 1.
Some sense we do that, but in a more advanced version in the weighted sampling that we do. Just this is in the same direction, but of course this is a trivial way to do it. We can do it more smartly as well.
Okay.
So you're saying that we can come up with in terms of bias, we can introduce more variables and that will blow up the little bit in the size, but bias will come into terms of number of variables and then we create it extractor. That's what we try to do here. Just try to see here what we are doing. Weighted sampling. So what is weighted sampling does is that each assignment has some probability associated with it. Each assignment. In this picture, I have two types of assignments. One has a probability 0.3, one has a probability 0.7. So of course, when I asked for the constraint sampler to generate the satisfying assignment, it generates proportional to its weight, its probability. And probability is proportional to weight. So we get more purple than yellow because 0.5, 0.7 for the purple, right?
So how are these weights given to the algorithm?
We'll see. We'll see. So what we are saying, for each assignment, there is a weight associated with it. And the probability of getting that assignment is directly proportional to its weight.
It's not quite. It's Bayesian, right? You can have maybe there were many more yellow satisfying assignments. There were very few purple satisfying
No,
assignments.
this is just saying that there is an underlying distribution on the satisfying assignments, and you want to sample according to that distribution. What is unclear is how the distribution is given.
That we'll see, but that's exactly what we are trying to do. So some distribution is given to us, and that underlying distribution you want to come up with a satisfying assignment. That's all. So now the question comes is that how are you going to assign weight to an assignment, right? What do we mean by that? And what we do in practice is this. We say that for each literal or let's say each variable, we assign some weight. What it says that x1 and x2.5 basically randomly between 0 and 1. Y1 I'm biasing it towards 1. You were saying, right? We can bias it towards. So that's what we are saying, that getting Y1 as positive should be 0.1, probability should be 0.1. So negative will be 1 minus 0.9, which is 0.1. And Y2 is 0.9 again. So what I can do, I can come up with a weight function with respect to each variable. And from that weight function with respect to each variable, we can calculate the weight of an assignment, which is nothing but the product of the assignment that we have in this, product of the valuations that we have in the assignment. For example, x1 is 1, so 0.5, x2 is 1, 0.5, 1, 0.9 and 1 minus 0.9. So what is the assignment of, what is the weight of this sigma? This is proportional to. So probability of getting this assignment is directly proportional to its weight. And there exist multiple strategies to come up with. Once we have this weights given to us, once we have the distribution, how to generate the satisfying assignment as per that.
And how would you come up with a good weight function?
Good weight function is heuristic.
How is phi presented to the algorithm?
Sorry.
How is phi presented to the algorithm? As a black box?
What is?
Phi of X, Y.
It's in the CNN formulation, right? It's a given as a specification to us.
Then sampling from its satisfying assignments is as hard as NP, at least NP.
Sharp.
Sharp field. So how are you to?
Practice we are able to do.
That is easy.
Oh, okay. Yeah.
SAT is very SAT is So once we know that SAT is easy, we can. Yeah. Talking about 2 QPF, right? Like I'm going to show that it is also easy. So let's see. So yeah, that's how we do. The thing that remains is that how do you come up with this weight, which is a heuristical approach. You have to look at your applications and see what is a nicer way with which you would like to generate the samples. Why I came up with this 0.5 for the input? Basically, for input space, we would like to have uniform distribution in some sense. Not like 0.5 will represent the uniform distribution, but in some sense, we would like to have uniform distribution in input. But at the same time, we would like to bias phi towards a certain value. And when we say certain value, that means it's 0.9 and 0.9. Manthan specifically come up with this heuristic and it tries to do that. It says that I'm going to sample certain number of satisfying assignment while biasing all towards 1. Then I'm going to sample certain number of satisfying assignments all towards 0. From that data, I will learn again what is the right bias. Because I don't know, I cannot understand the problem statement. As per Manthan, for it, the problem statement is a black box. It does not look into the structure of the problem statement. So for the Manthan, how it's going to come up with a nicer weight, that's how it's going to come up. It says that I don't know, I'm going to sample the satisfying assignment biasing towards 1. I'm going to satisfy certain assignment biasing towards 0. I will have both the data and I will learn what is the right bias which I should sample. This is just one heuristic. We can just start with this also. Learn candidate function, we can start with this also. Just one heuristic. That we have seen that it works well in the practice. And as we were talking about, SAT is easy. SAT is all about different heuristics that works well in practice.
So why do you start with a different weighting function? I mean, so what is the intuition behind having like 2 different things and then
1 towards 0 and 1 towards 1. So basically it says that the first word, when we are, even though we bias towards 1, for a particular input, if it has to take value 0, it will take value 0, right? We are not trying to ask for a, indeed we are generating satisfying assignment, right? So whenever it has to take value 0, it will take value 0. So similarly, even though we are biasing towards 0, whenever it has to take value 1, it will take the value 1. So from that data, we'll say that how many times it had to, like compulsorily had to take value 1 and had to take value 0, and then we decide our bias. That's all. We're not doing anything fancy. And this is just this is the slide to, and these are the references who all are interested and intrigued by this constraint sampling, weighted sampling, and so on and so forth. Please, these are multiple different ways of doing it, and you can go and check. some theoretical guarantees also. This hashing based techniques has theoretical guarantees. Rest all does not have it.
That's a good question, but suppose I input this factory relation in a SAT problem and
Sorry?
suppose I input the factory relation in a SAT problem and give it
But-
to the
Factorization will fix the number of bits, and
yeah.
then accordingly we can convert it
Yeah,
to
yeah,
state
so
and then it
input
comes.
into a SAT problem, then this algorithm should fail, right? When-
Up to 14 bits we are able to do it.
I mean, is there any reason that for other real world instances it succeeds, but for this particular instance?
Still, SAT is also not able to crack SHA, right? So, but that works well for the other instances. So, it's just the property that we see in these industrial benchmarks are not as hard as the. So, whenever we do this analysis, is with respect to the. I'm talking this in front of theoretical theory people, but please.
Is there a conjecture property?
We don't have that, and that's an open question. Is that so? We have studied with respect to knowledge representation some techniques like some structure is there, then it's easier and all of those. But we don't have we cannot check whether the industrial benchmark have this property, hence it is easier to do it. That's not true. We have studied with respect to the knowledge representation, even the SAT solvers, maths, this sampling and all of these. We try to look into different forms of like how are we going to represent the form, like they satisfy certain property. We can show that it is easy, but we cannot show that this is why the industrial problem is we are able to solve it. That's not it's not clear. Yeah, but the knowledge representation based technique is all about the properties in the structure. And then they try to extract that property and use it with respect. So these are the set of work that we have done in this direction. Okay. So we have generated some data. Now the next part is to learn candidate function with respect to those data. So suppose you wanted to learn y1, what we can do, we can use the features of x1 and x2, valuations of x1 and x2 as features, and valuations of y1 as label. We can pass it to the decision tree and they can learn a function from that. For y2, what can we do? x1, x2, y1. We can use that as a feature and then pass it to them. So that's how we can learn, right? When I say from the decision tree, we can learn a candidate function. What will be a candidate function once we have a decision tree? We look into all the path that leads to leaf node 1, and it's basically the disjunction of those paths. Right? This is my candidate function. It's going to be like that. There are two questions here. One, so this data that we have generated, all are satisfying assignments, right? There is no error. Error in the sense when we talk about machine learning algorithm, they say that the classification is wrong. For some input, the classification is wrong. That is not the case here. This is all satisfying assignments. Whenever, so this y1 is, whenever it is taking value 1 or 0, they are going to satisfy the specification. There is no error in this. So we have this trustworthy data. What should we do? Should we overfit on this data?
That sounds fine.
We can sample, add some, like just sample randomly.
So we have generated the data. Let's say we have sampled 10,000 data points. We have that 10,000. Now we are not going to sample again. We have the 10,000 data points. We are learning the function. On those 10,000 data points, there is no error. So basically, we have this trustworthy. Every row is a solution to the field.
The learner will think everyone is telling.
Sorry.
The learner may think.
So that is the machine learning way, right? Like, so that's what we do. So machine learning, we know that there is some error. So we tune it with respect to that. So here we know that there is no error in the data. In ML algorithm, usually we know that there might be some error. So we try to tune it with respect to that. So training error, testing error, and all of these are there from there.
We add some random variables, so before training, exactly for.
This might be, I haven't tried it, this might work. Well, because in these kind of setting, until unless we do experiment, we cannot say that whether this is going to work or not. But one thing that I can for sure say that this is like a subset of the data, right? Suppose hypothetically, if we have thousands of variables, then 2 to the power 1000 might be like the solution space might be that large, right? And I'm just going to sample 10,000, 15,000. So this is just a subset of the data. This is not the entire truth. This is not the entire truth table that we have. It's just a subset of the data. So what we do is that we don't learn abstractions, we learn approximations. And in that, what do we mean by that is that we are allowing them to make some error in the data that we have. We don't overfit on the data. We say that up to this depth, you learn the candidate function. You don't overfit. Don't like balance tree. Finally, you get one lead. Don't try to learn by that one. Why? What is the intuition? The intuition is said that if we just overfit on this data, we don't know about the remaining data points. So we say that in order to generalize over the data that we haven't seen so far, let's just make a scope of error here as well. If it is going to be consistent with the other data that we haven't seen, we just need a couple of repairs and we are done. If that is not the case, this error might help us in the future. So that's the picture. So we don't overfit on the data.
I don't get your point. Why should we not overfit your data?
Because
there is no noise in data, right?
Yeah, exactly. There is no noise in data, but at the same time, this is just a subset of the solution. So from 2 to the power 10,000, that can be the number of satisfying assignment. We just have 10,000 satisfying assignment. So but finally this column function has this property that for all x, the function should satisfy the specification.
So basically, you don't want to make this tree too deep or something.
In some sense, we don't want to overfit. Overfit means that the tree is there, right? Like it has balanced and come to a certain level here. That's what we don't want to learn. And when we say approximation, basically we have this kind of a two-sided errors. We don't have one-sided errors. So for some input, my candidate function can say that, oh, take value 1, but the actual value can be 0. And similarly, for the same input, my candidate function can say that take value 0, but my actual value can be 1. So there can be two-sided errors that we have to repair. And usually in the traditional approaches, we learn abstractions. For example, the trivial over abstraction is like set y1 is 1, always. So there is always one-sided error. Whenever y1 has to take value 0, that is a one-sided error that we have. So that is what in the traditional approaches, cigar-based approaches we do, which is like counter-example based abstraction refinement. In refinement and abstraction, we always have one-sided errors. But what we have learned is approximation and we have two-sided errors. So we are not going to refine, we are going to repair.
Why is that blue?
Huh?
Why is the A blue?
Sorry?
Why is the A blue?
Abstraction
Oh,
and approximation.
oh, okay. Also, one more question. So you have generating these samplers and you have some process of doing it. Would it be better to have your verification procedure generated? You start with some samples, you come up with some things that does not satisfy, and then you use it back to improve.
That was one thing that we tried, and what we noticed is that in order to be, the candidates are very good, so we require very less number of repair rather than you sample again, append into the data and relearn. So that was more costlier than just repairing and get done with it. But that can be one way of doing it as well. Okay. We have learned the candidate function. I have 5 more minutes to finish this, so let's just try to do 5 minutes, okay. So verify and repair, right? So what are we going to verify? Verify is that for all x, whatever we have synthesized, that satisfies the specification. So this is Supratik and his group came up with this formula called error formula. I'm just going to use their terminology here, and we are also going to call it error formula, though I won't agree with the name. It's not fancy enough. So we have this specification. Y prime is basically nothing but the functions that we have synthesized. And we have this negation here. What it says that, you remember the check that we had was a QPF check. For all x, there exists a y such that the specification and so on. So we wanted to verify it with respect to a SAT solver. So that's how we do it. We say that if this formula is unset, what does it mean? That for all x, wherever there exists a y, whenever we replace this y with the function that we have synthesized, they also satisfy the specification, hence this negation will make it unset. Just stare it for a minute, you will realize. So whenever this formula is set, for the same x is same in these two versions, right? So for the same x, there exists a value y that satisfies the specification x, but the synthesized function do not satisfy the specification. So if the formula is set, we have a counter example. If this formula is unset, we know that we have synthesized column functions. And this is the SAT call that we are going to do for the verification.
I'm facing a difficulty in type. So the y prime is not a boolean, like a boolean value, whereas fx is there.
Fx
So fx is no, so y is implied there. Actually, neither of them are.
Just y prime is equal to x.
equal to
X. Equal as a vector.
X.
Ah.
That's it. It's a vector. Yeah, of course. Y1 is y.
Yeah.
M inputs, n inputs, m outputs, each fi, all of these are there. Okay, suppose we got a counter example, sigma, that satisfies the specific, this error formula that we have. And this might look like this. It says that whenever x1 and x2 are 1, one of the possible assignments for y1 and y2 can be 1 and 1. But our candidates column function are giving it 0 and 0. So that was a counter example. So what should we repair? We have two column functions, one corresponding to y1, one corresponding to y2, right? Two decision tree we learned, and we have post column function. So which one to repair? Both. What should we do? Should we repair both? But remember,
The other one.
it came there.
The network is.
So, of course, we can repair y1 and y2, but remember this is a relation again. For the same input, it might happen that y1 is 0 and y2 is 1, and that also satisfies the specification. It might happen. Well, in that case, you don't want to repair our candidate function corresponding to y1. You just want to repair candidate function corresponding to y2. Because we have a relation specification, this might happen. So we don't know. But we got this sigma as a counter example. We have no idea whether sigma hat exists or not. So we can pose it as an optimization theory. We try to find nicer counter examples. What can we do? What do we mean by nicer counter example? Sigma hat, where we have lesser number of repairs. So we try to find out the nicer number of counter examples. And how can we do it? By posing it as an optimization theory. We see that specification, we have fixed the input as per the counter example that we got. But at the same time, we are trying to maximally satisfy this output of this column functions that we had with respect to same input. This is a max set problem. How we do it in the practice, this is max set. These are our hard constraints. This is my soft constraint. We try to satisfy, we want to find a satisfying assignment that satisfy all the hard constraints and try to maximally satisfy the soft constraint. This is a max set problem. We do have nice max set solvers available. So from there, we get our counter example, we get our candidates to repair. And once we have the, once we have figured out that we want to repair y2, we ask the reason why whenever x1 and x2 is 1, x1 and x2 is 1 and y1 is 0, y2 cannot take value 0. What is the reason behind it? And that reason, we explore it with respect to the unset. That's it. So this is one thing. We have the specification, we generate some data using constraint sampling. Once we have the data, we learn candidate function using decision trees. Once we have the candidate function, we try to verify using SAT solvers. If the SAT solver says that there does not exist any counter example, the formula is unset, we have our function. Otherwise, the function goes into a repair. So this is one thing for us.
So the error, the E function that you had, so that depends on whatever was the scalar function that was generated previously, right?
But then we repair it and then the new function.
That keeps changing. Okay.
Yeah, here we are passing this again.
I see, okay.
Again, this was all about heuristic, we want to scale and so on and so forth. So let's see the experiment results and then conclude it. I got it there, so I'm just waiting for it. Yeah, here it is. So this was the state of the art before Manthan. So we compared over 609 benchmarks arising from, there is a competition, you were asking about the benchmark, so there is usually a competition happening.
But we don't have factoring of it.
No,
Okay.
of course. We still have time. So
I mean, if someone could break it, do you think they'll be playing the benchmarks as opposed to?
So we have total of 609 benchmarks. We gave a timeout of 70 to 100 seconds, which is 2 hours, to finish the solvers. Before Manthan, the state of the art was CADIT, BFS, and C2SIN. CADIT was from Berkeley, and BFS and C2SIN from IIT Bombay, Supratik, Akshay, and their group. And these 3 tools are very different. Basically, the CADIT is incremental determinization, SAT-based approach, how the SAT solver tries to find a partial assignment and try to prepare. The CADIT does that. And BFS and C2SIN is knowledge representation-based approach. They try to convert, they try to see the structure in the specification and try to extract out the function based on the structure. So, and out of 609, the CADIT was the state of the art, which was able to solve 280 instances within the timeout of 70 to 100 seconds. This plot that you are seeing here, the x-axis is the time taken and y-axis is the benchmark. And a point xy represents that, a point xy represents that each of these y many benchmark took less than or equal to x seconds to solve. Right? So that's how you read it. Now, where does the Manthan stand? We were talking about scalability. It came nicely. I thought I have to give time. So here is the Manthan. Manthan is able to solve 509 instances out of 609 that we experimented with. And that is a state of that the benchmark set was standard that was used when C2SIN was proposed, BFS was proposed, and CADIT was proposed. The same benchmark set we tried to do experiment. And you see there is a little more time we were taking at the beginning where all 4 of them were solving. This is because we are generating the data and then learning time decision tree with respect to each Y. So it's a time-taking process, but at the same time we are able to solve more benchmarks. So this here, a little bit green as you can see here, it's because of the decision tree-based algorithm, because we are learning decision tree for all possible, all outputs, one at a time. We are working on parallelly running and all of these, but interdependencies are the problem. So this is Manthan for you.
Wait, so the time to do that should be independent of the instance. It should only depend on the number of variables or something.
But the structure is also important, as you were correcting me at the beginning, that not just the number of variables, factorization counts. So the structure is also.
Because
Thank you.
that's my
So, before we conclude, these are some of the future work which we are looking into. Basically, verification from abstraction to approximation, can we just come up with more techniques there? Propositional synthesis, we were just restricting ourselves to the 0-1 Boolean domain. Can we go beyond that? From learning theoretic point of view, we don't know what is the ideal distribution to generate the data. We have no idea towards that. And we don't know the mistake bounds also. Whenever there is a functional data is there, we know how many samples are good enough and what is the lower bound and all of this. We have no idea about the relational specification. So that is also an open problem. And of course, this venture when the FM formal methods and AI comes together to do wonders. So with that, I would like to conclude and I'm ready for these questions.
I have to go.
Yes.
Will you go back?
Yeah. Where?
The previous slide.
This?
Yeah. So this data, the weight generation phase in your algorithm.
Yeah.
Is this also something that tools like tools for machine learning could help, or is this
Sorry.
the way you generate weights? you want a weight which has certain properties that helps you do things better in the future. Is this something also that can possibly be done by machine learning type things? It sounds like a.
So
I don't know,
when I
it
said
sounds
that
like an
we are
ML.
learning, right, what is the right bias, that is what we are trying to do. We sample but one towards biasing towards one and one biasing towards zero, and then from that data. We are trying to do that only, we are learning the right way. But that is one heuristic that work well for these benchmarks. So whenever we say that, oh, Manthan is a state of the art, that is with respect to these 609 benchmarks that we experimented with. So we cannot generalize, so that's why we call it heuristic, right? We don't know whether this machine learning based approach of coming up with the right bias is the right way or not. But yeah, one way of doing that is.
And in the previous, on the previous slide, you have this graph. So, like a lot of techniques that you described were techniques that probably were used in the formal methods literature before, and maybe some of these other works also used it. So fundamentally, the thing that I learned about your thing is the ML subroutine at the beginning of the.
Is two things. Of course, ML subroutine, because we were able to come up with nice guess and then complete it. And another thing is this approximation and abstraction thing. So all the approaches were cigar-based method. And because we were using ML, we realized it later that, oh, it's an approximation and we have two-sided errors and hence we have to change it in our repair base. One slight plot that I wanted to show was this. This is the same set of benchmarks, and these are basically different samplers, basically different way of sampling the data. Remains just one constraint sampling part was there in the method, just change the underlying black box sampler. Remaining all is the same, just sampler we have changed, and you see the impact. So data is important. Here we are doing this weighted distribution, and this is uniform distribution. So different. So data is important, and still we don't know the right distribution. This is just one heuristic that worked out, right?
This graph is inverse of that graph.
Yeah, it's just mirrored. I should have done that. It's just the benchmark was on y-axis, now we have so I should have corrected that. This is just one, the optimization that we did, right? Like we did not repair it with respect to the counter example that we got. We said that, oh, I'm going to look for the nicer counter example, optimization problem and so on. This is the impact with respect to that. And this is abstraction versus approximation. So here we just fix that, oh, whenever y is, I just fix that either it's going to fix to the 1 or it is going to be fixed to the 0. We are not going to learn anything. We're just going to start with respect to that, and this is what the difference between currently, like just the decision tree. So basically, each part of Manthan is important. That's what I want to do.
So in the special case when, for example, you have the specification where there is no X, you only have a Y, in which case then you are truly just doing SAT solving.
Yeah.
Right, you're just basically asking.
Right?
So for example, can this be, I mean, does this help you build better SAT solvers? Like in the sense, because SAT solvers also have a very similar structure in the sense that you start with a potential guess and you're hoping that there are few changes that you need to do, like you freeze variables and you still. So for example, does this help you construct better SAT solvers?
SAT solver we did not experiment, but the machine learning based guess and then repair, the Monash University, the people, they are trying to come up with this neurosat and all of those, where they try to come up with satisfying assignments. SAT solver basically based on machine learning approaches. The problem is that why community is not happy or why we are not happy about it is that the machine learning algorithm does not give you guarantees, and whenever we use SAT solver as a verification task, that's the bigger, like that's the application with which we sell SAT solvers, right? So if it does not provide a guarantee that the assignment that is getting, it's the right assignment.
No, I again, even here.
They were not repairing. So the neurosec that they try to do is just that they use machine learning algorithm to come up with satisfying assignment fast enough. So they are now
looking to use an ML subroutine to just find the starting point and then start the whatever the branch and bound sort of a thing from there. Even here, something similar is happening.
Yeah,
right?
exactly, it's
Yeah.
the same thing, but yeah, I'm not aware of it, we haven't discussed, the neurosite, maybe the previous work, they have tried it and maybe they were not able to see it. So the neurosite is a SAT solver that is available, which is basically neural network based SAT solver. And they do nice heuristical approaches to it. And another way the machine learning is used in SAT solver is like coming up with this heuristic, which you were saying that, which heuristic works very well. Like there are many heuristics are available for the SAT solver. Which one to pick for a particular benchmark that are also they're trying to decide. So this is all the.
I have a question.
Yeah.
So can you just go back to the previous slide?
Yeah.
So in these benchmarks, are there a set of inputs and outputs and constraints which?
The relational specification amount.
And
So when I say benchmark, it is basically one particular instance where the relational specification between input and output is given. So we had such 609 instances.
given enough time, will any or will all or which of the?
All of them are complete solvers. So if you give infinite amount of time, they will eventually converge.
So if I wanted to do experimentation with respect to not and or not, but say I also allow linear things. And then again, like instead of SAT solver, you could do the second step or with the MILP, which is also quite like, popular, very developed. So there's that, and then the point that is the machine learning step could be replaced by something more like something not stronger but maybe more principal than vision trees, like.
Yeah, SVMs, and so when we talk about linear real arithmetics, we decided to work with SVMs because again, a decision boundaries and the similar support factor machine, we get efficacy. We were not able to scale. The reason was, here there is a lot of
But I think
optimization.
it is something much simpler than it. Just
The data sampling point that we have,
is only.
constraint sampling here, for the Boolean, we have fabulous solvers available which scales really well. Unfortunately, at this moment, we don't have a nice sampler available for this. Bit vector, of course, we have, but not with respect to the other, which scales to the.
Oh, because the translation from the linear classifier to Boolean loses the law. Like you could do that.
That is not going to scale. So bit vector, we tried and doing that. This is easier, you can always see. So there is a lot of in processing and processing goes on. Otherwise, the formula becomes very large. So that if we just don't do this in processing and processing, we are not able to scale even with the one stage. With that. So that's where, and if you do this processing, you lose the essential sense of the initial formula. Some of the constraints will be like, so that's where how to do it nicely is still a question.
Have you tried biasing different affine spaces instead of just x1 to xn? Have you tried biasing different affine spaces instead of x1 to xn? Why not bias x1, XOR x2 to something?
Why not bias x1 and try to
x1, XOR
Basically,
x2.
do a linear transformation.
Yeah.
we can
That's what I was. Yeah.
yeah.
And so the SAT solvers that are generally there, like for example, if you want to pick up a solution according to a certain distribution, just sampling the first point according to a related distribution alone is not enough. Or like I mean, like in the sense, I'm curious to know how these whatever samplers sort of work, because I can understand SAT solvers is something that is that's trying to just pull out a satisfying assignment. Okay, I'm willing to say that okay, NP is equal to P.
No.
I mean the practical word or whatever. But counting the number of satisfying assignments seems like a way harder question. So
Stop.
No, I agree.
But that's what it does. Sorry, that's what it does. Stop math. And like approximate counting is in the second level. If you have an NP, you can do approximate counting.
Oh,
I
Yeah.
oh, I see.
So the samplers like in the meal work and so on. So they are based on what is in obviously called the Stock-Myers theorem, which shows that approximate counting can be done with access to an NP.
Yeah. Via hashing. So that's what I was saying, that you divide the solution space via hashing and you assume access to an NP oracle, and then you try to count the number of satisfying assignment in that small region and multiply by the number of resources. So again, you need guarantees and all.
We only need approximate count, not
Exact also we can do. There are exact counters also available.
Yeah, but they will not be
No.
They will not help you. They can't. Because then,
No, because even if P equals NP, Sharpie could be different.
you can't do exact counting. Exact sampling can in certain situations work, even because exact sampling does not let you do exact counting. So exact sampling is in terms of counting is only as powerful as possible.
But in certain properties, if we can knowledge representation, they say that if there is a certain structure.
Yeah.
If there is a certain structure, and if you can reduce your benchmark into the certain structure, then you will be able
So, for
to.
example, if the stat form, like you can do the constraint.
And in forms, yeah,
Like a tree, then
you
you
know.
can.
BNN forms and all of those. So there is again Pradeep's work with the student called Shubham, where is the founder name, which tries to see that if the formula is under a certain form, they convert it and gives you the exact content, which is very efficient.
Exactly. Yeah. So exact counting you require some stuff.
Some structures. So I know that this more was more like a practice talk than a theory talk, but hope you enjoyed.